Section 5.2 is definite integrals. We're going to just briefly revisit the sigma notation, something that you should have seen already. So again, refreshing our memory, this is the sum as k goes from 1 to 10 of a sub k, where a sub k is any term in the series. So we starting with 1, we go a sub 1 plus a sub 2 plus a sub 3, all the way until we get up to a sub n, whatever it may be. I'm going to tie this into our definite integrals. We've been doing an integral as the sum of a bunch of rectangles. So the existence of definite integrals. All continuous functions are integrable. That is, if a function f is continuous on an interval ab, then its definite integral over ab exists. So basically saying that any continuous function from a to b will have an integral or an area under the curve. The definite, sorry, that's a little bit off the screen. The definite integral of a continuous function on AB. So let f be continuous on AB. We already said that that means that the integral exists. And let AB be partitioned into n subintervals of equal length called delta x. So in other words, delta x is going to be the distance from A to B divided by the number of intervals we want. Then the definite integral f over AB is given by this sum notation. So we're taking the sum as k goes from 1 to n, and we're looking at the limit of those sums as n approaches infinity. So in other words, again, I'm taking from A to B, and I'm doing rectangles, and I'm going to split that up into n divisions, which means each subinterval, or our delta x, is b minus a divided by n. And we're taking the limit of that as n approaches infinity. So as these rectangles become smaller and smaller, and as we do that, we're taking the sum of each one of these rectangles. F of c is the height of the rectangle. Delta x is the width of the rectangle, where c sub k is chosen arbitrarily in the kth subinterval. So in each interval, we are choosing some arbitrary spot that we are going to use for the height of each rectangle. So that's the sum notation of an integral. And then we have our integral notation. So this is read as the integral from a to b of f of x dx, or sometimes as the integral from a to b of f of x with respect to x. So we have our sum notation as the limit of an infinite number of rectangles, and we have our integral notation. So again, another diagram with the pieces. This is all stuff you did last year. The integral symbol, the lower limit and the upper limit of the interval of integration. The function is called the integrand. This is the variable of integration. And when you find this entire value, you have evaluated the integral, which again we know is the area under the curve. So here's an example using different notation. So the interval -2 to 4 is partitioned into n subintervals of equal length, delta x being 6 divided by n, because the interval from -2 to 4 is 6 units long. Let m of k denote the midpoint of the kth interval and express the limit. So the limit as n approaches infinity, as our divisions become greater and greater, and therefore our rectangles narrower and narrower. The sum of all of these functions, there is our height, our function value, that's the height of each rectangle, times the width. So we're adding up all of the rectangles, areas, length, or excuse me, height times width. And then showing that this then transfers to our integral notation, sum notation here, and integral notation here. So this integral is very similar to talking about our sum. It's implied that our dx's are approaching 0, that our width of our triangles, our delta x, as n approaches infinity, is approaching 0, so that's implied in the integral notation. So what is the definite integral? Well, it's the area under the curve. So if y equals f of x is non-negative and integrable over a closed interval ab, then the area under the curve from a to b is the integral of the function. So again, just tying together the two ideas that area under the curve is the definite integral. So area is the integral, and this is, oh, I'm sorry, they're doing the opposite now. When the function is below the curve, when the function is less than 0, then the integral is the opposite. We'll remember that from a to b. So this is going to be a negative area. The integral from a to b is the area above the x-axis minus the area below the x-axis. So here's a pictorial here. If f of x is a constant, then the integral is just c times b minus a. And there's one above, there's one below. So the last thing we're going to look at in this section, because we're not actually working with antiderivatives yet, is NINT. And just to refresh your memory, go in quickly and find the definite integral of this using some calculators call it FNINT, some calculators call it NINT. But go in and see if you can remember how to do that. I'm sure you do. And that's it for our video.